Hi everyone, this is Soshin. I am making a video on chapter 4, the first proof, which is found on page 7. Now this proof is about the new definition of the Poisson process that we introduced in chapter 4. And essentially it comes down to proving that this new definition amounts to the same definition as the definition of a Poisson process that we introduced in chapter 1. So let's take a look at what this proof is saying. Let's start off by recapping this new process that we define in chapter 4. So we're saying, let's suppose we have this process NT with a filtration FT. Okay, now remember that a filtration just means the past history of the process. Okay, so FT in this case just means all the previous values of this process NT for each of the time points before and including time T. Okay, so we're saying this is a Poisson process. Okay, so is a Poisson process if, and here's the definition we are giving it. We're saying if the probability of a jump in h time units, so the difference between nt plus h minus nt, if that jump is 1, in other words, if it can jump 1 in h time units, given all the past history of the process, so given a filtration t, sorry, let me just correct that, then we give this event a chance of happening of lambda times h, so some parameter times the time unit, okay, the time interval, and then plus O of h. Okay, so the idea here is that if we start making h small enough, we can then start assuming that that O of h is going to 0 faster than h goes to 0, and therefore we can only make this one move in h time units. Okay, so then another part of this definition is saying if we take this difference, nt plus h minus t, and say that there's also a chance that that jumps 0. In other words, the NT doesn't increase in that time interval h, given all the past history of that process. Then we say this is 1 minus lambda h plus the O of h term. Okay. And then finally, we're saying the chances that it's anything else, in other words, nt plus h minus nt, if it's not 0 or not 1, okay, then, yeah, so maybe just to write, maybe I'll write it slightly differently, if that it's not an element of the set 0, 1, something like that, right? Given ft, then the chance that this happens is just O of h. Okay, so in other words, when h gets small enough, we can ignore the possibility that this process, the increments of this process in that h time units is neither 0 nor 1. Okay, great. So this doesn't look anything like the chapter 1 definition, which was saying, you know, we start the process at 0, we have independent increments, and then the increments follow a Poisson distribution. This is not saying that at all, okay? So we have to prove that. So we're going to start by our first claim, right? So claim number 1 is that we are saying that NT is a Poisson random variable with a mean, in other words, the Poisson parameter of lambda t. That's our claim. And now we are going to prove this claim. Okay, so let's look at the proof here. And there is a more general result, which I'll come to after this proof. But for now, let's just think about NT. Okay, so for notation, let's define Pj of t is simply a short way of us saying that it's the probability that our process at time t, which is nt, is equal to j. In other words, there were j jumps or j counts happening in the time, in the t time units, okay? So exactly j events happened by time t, okay? We know what that means. So all we need to do now is we need to say that if we can show, so to prove here is that this thing here, pj of t, which is the probability that nt is equal to j, has the same PMF, because we're dealing with a discrete random variable, the same PMF as the Poisson distribution, which is e to the minus lambda t times the rate, which is lambda t to the power j divided by j factorial. Okay, so if we can show that, then we're done with this first claim of the proof. Okay, so we simply now consider what happens. We need to get to a formula. So we do this by creating a differential equation and using the boundary condition of what happens at time 0. Okay, so those are the two things we do. So let's start off with the derivative. Okay, so creating a differential equation. To do that, we need something that looks like pj of t plus h, so that we know we can take pj of t plus h minus pj of t divided by h, and we can use our first principles understanding of what a derivative is. So we need to say what are the possible values of j and what are the possible values of t. Okay, so of h. Okay, so let's consider that for any j that is bigger than 0. Okay, let's see, and let's take h as a small time point. So and for small positive h, right, what do we have? So we have that pj of t plus h is, well, what is this defined as? This is just the probability that nt plus h is equal to j. Okay, now let's look at the ways in which this could have happened. So I'm going to draw myself a quick timeline here. So if I say from time t to time t plus h, I want I want j events to have happened by time t plus h. So because we're thinking about a small time unit h, there's only two possibilities here, because we're saying we can make h really small so that, let's say there was only one jump. I mean, that's loosely what we're doing, but even if we're not, we're still having this O of h term, so we don't need to worry too much about it. But the point is that at time t, we could either have been at already j events have happened, or we could have had j minus 1 events having happened by time t, and then the other jump happening between times t and t plus h. Okay, so there are two possibilities. So now I'm going to write out those two possibilities where there was only one or 0 jumps. Okay, so the possibility that there were 0 jumps in those h time units can be expressed as this. It's the probability that nt was already equal to j. Okay, so nt was equal to j, and so I'm just going to write and as an intersection there, and the event nt plus h was also j. So in other words, that was just the same as nt. So that's my first possibility. And then my second possibility is the possibility that I was at j minus 1 events at time t, and then between time t and time t plus h, I had another event occurring, and therefore my nt plus h went up to j minus 1 plus 1, which is j. So that's the probability that nt was j minus 1 and nt plus j was equal to, nt plus h was equal to j. Okay, in other words, that was equal to nt plus 1. Okay, so that's my probability there. So those are the two events, and then because I need to account for the fact that maybe there were more than one jump, so maybe at time t we were at J minus 2 events and stuff like that. So then I would consider all of those other possibilities as O of H, because I'm eventually going to make H small enough so that I only really need to pay attention to the 1 or 0 jumps happening in that time unit. Okay, so if I just write this out, then this becomes, what is the probability that that NT was J? That's just PJ of T. And then in the NT plus H time units, remember from the way we defined this NT plus H here, it doesn't actually depend on any of the past of the process. So I can multiply. So these two events, I can multiply their probabilities, right? And then what's the probability of this guy here, the NT plus H equal to NT? Well, that's just the same thing as NT plus H minus NT being equal to 0. Okay, so this is the line we're thinking of here, and that's just 1 minus lambda H plus O of H. Okay, so I can substitute here 1 minus lambda H, and then the plus O of H, I'm going to add it all at the end, so I can ignore it for now. It is there, but I'm going to add it right at the end of this equation. Now let's work on the second term. This is just, again, two independent events. So Pj minus 1 at time t multiplied by, now I'm looking at Nt plus H is equal to Nt plus 1. So in other words, Nt plus H minus Nt is equal to 1. And therefore, I am looking for this line of our definition, which, and that probability is just lambda H. So go back here and I can write times by lambda H, okay? And there I now need to pay attention to my O of H terms. Okay, good. So now let's rearrange this equation, okay? Some just really elementary maths here will allow me to take Pj of t to the other side. So let's do that quickly. So I get Pj of t plus h minus Pj of t, okay? That's the minus there. And now I'm just going to do it all in one step. I can also divide by h. Let's see, can I divide by h? Yeah, so just do this. Okay, so I'm going to say, I'm going to take that and divide by h. So now I'm taking Pj plus t of t plus h minus Pj of t, which don't have any h's, and I'm going to divide by h, and then I'm going to be left on the right-hand side with minus lambda. Okay, so that's this minus lambda times h times Pj of t divided by h. So it's going to just be minus lambda times Pj of t. Okay, and on the right-hand side here, I'm just going to be left with lambda times Pj minus 1 of t. Okay, plus lambda times Pj minus 1 of t plus all of those, and then all of those terms end up getting divided by h as well. So now when we take our limit, so if I simply say taking limit as h tends to 0 on both sides, then I'm going to get on the left-hand side, I'm going to get, well, d by dt of this Pj of t, this function, right? And on the right-hand side, I'm going to get is equal to minus lambda Pj of t, because that doesn't depend on h, plus lambda Pj minus 1 of t. And then this part here, as I take the limit as h tends to 0, by definition of O of h, that ends up being 0, okay? So that quotient ends up being 0, and I can just write that. Okay, now, what about an initial condition? So, and we have an initial condition. Okay, what does that mean? It just means we need to think, in addition to this differential equation, we know stuff about what happens at time 0, because this is a counting process. So we know that at time 0, the chance that there are j events and 0 time points is actually 0. Okay, because we know that this process must start off 0. How do we know that? Go back to the way we've defined this thing. And you can see here that if you are thinking about the time point 0, in other words, n0 minus n0 will come up with that line there. And h will be 0 in that line, right? So the chance of that happening is 1 minus 0. Similarly, you could see it in, so in other words, nt has to be 0. Or you can see it by looking at the top line to say, if h is 0, in other words, we're looking at nt plus 0 minus nt, and specifically we're looking at time 0, so therefore we're looking at n0 minus n0 is equal to 1. The chance of that happening is going to be 0 because it's just lambda h, right? Lambda times h. So we know that the pj of 0 has to be equal to 0. So that initial condition makes sense, and we have to have that. Okay, by the way we've defined this process. Okay, cool. So let's continue with this piece and see whether we now remember what we needed to prove. This is what we needed to prove. I'm going to highlight it in blue here. We needed to show that pj of t follows this equation. Okay, so in the notes they call this equation 4.2, so I'm just going to stick to that. So let's test equation 4.2, right? So just write this in a different color. Let's say blue. So now test equation 4.2. Okay, so we can test it quickly. What is pj of t? So if we know from equation 2, pj of t is e to the minus lambda t times lambda t to the power j divided by j factorial. Okay, so let's test if we can tie back to this equation for the derivative. Okay, so just to shorten it, we'll say pj prime of t is what? Well, we can use a product rule here. I'm going to get e to the, this is my one, let me just show it like this. This is my one, you can think about this as your one factor and think about that other one as your other factor, okay? Or you could just take out the 1 over j factorial because that's a constant. However you want to do this, it's quite easy to do. So what I will do is I'll just take my derivative now of the first function, which will be minus lambda times, and then everything else stays the same because my derivative of e to the minus lambda is just e to the minus lambda t, and then I've taken that minus lambda and multiplied it there, divided by, and then the second factor stays the same, so that's lambda t to the power j, and then that constant also just stays there. And now I have to add the first term multiplied by the derivative of the second term. So the second factor, so that second factor which I'm regarding as that, the derivative there would be lambda to the j times t to the j minus 1. And then I have to take the derivative of inside the bracket, which will then be lambda, because I'm using the chain rule there. So I'm going to get j times lambda. So I'm going to get lambda times j, right? And then that's going to be lambda t to the power j minus 1. Okay, so that's lambda t to the power j minus 1. And then I'm just going to multiply by what's remaining there because the other factor stays the same in the product rule. So that's multiplied by e to the minus lambda t over j factorial. Okay, cool. If I have to just simplify this, I'll go to the next. Actually, I could probably just put it in here. So the first one is, what is this first term here? It's you can see this is looking like just Pj of t, right? That's the formula for Pj of t that we're trying to test out. So if we are given Pj of t, as we are on top there, you can see that those look exactly the same. So I can just rewrite this as minus lambda times Pj of t, right? And on the second term, I've got what? Let's see. This j here is going to cancel with one of the j's there, and I'm going to be left with j minus 1 factorial at the bottom. Right? And then I've got so what do I have? I've got e to the minus lambda t times lambda t to the power j minus 1 divided by j minus 1 factorial, which, as you can see, is just pj minus 1 of t. And then I've still got that lambda in front there. So after simplification, what I'm going to get is plus lambda times pj minus 1 of t. And that's it. Now so we've checked now that this top one works for the general case. Okay. Now let's check that this initial condition also holds. Well, we can check that quite easily. So let's write that out. Now check initial condition. Right, so let's check. What do we get when we take pj of 0? So the initial condition is what happens when we take pj of 0, and we want it to be equal to 0. So let's plug it into this formula. Well, we're going to get e to the minus lambda t, so that's going to be e to the power 0, which is 1. And then we're going to get lambda times t, which is going to be 0 to the power j. So you can see that we are going to get 0 as required by the initial condition. Okay, cool. And the notes actually just expand that out a little bit to say you get e to the minus lambda times 0 times by lambda times 0 to the power j. Great. Now, so let's just go back to our proof of claim 1, right? So we said all of this was true for this situation here. Any j greater than 0 and small positive h. So I'm going to say here, we are done with the case j greater than 0. Okay, so now, and if you wanted to, you could write this as case 1 here. Okay, so the case 1 was j greater than 0. Now, for the rest of our proof, we have to deal with the other possibility, which is that j could be 0. So let's say case 2, j equal to 0. Okay, what happens in this case? Well, we can go back to this previous line. Remember, we said that we came up with this equation here. So similar to what we did for case 1, we have, okay, so we have this equation here, derivative, this one here, okay? So it's the derivative of pj of t is equal to minus lambda times pj of t. So let's just write this out, the derivative of p, now we're looking at the case where j is 0, so derivative of p naught is equal to minus lambda times p naught plus lambda times p j minus 1. Okay, so now, okay, so maybe that's not going to work out well for us. So let's just redo it from scratch. Okay, so this is what happens when we when you would do a proof, you would end up figuring out that things are not working as neatly as you'd like. So we would just go back to first principles here, right? So what is P naught of T plus H? Okay. So I'm redoing the method we used for case 1. Okay. Well, that's just going to be, as we defined, the probability that NT plus H is equal to naught. Okay. And what are the possibilities here? Well, there's only one possibility. If in T plus H, you had 0 events happening, then there is only one possibility, which is the probability that at time T, you had 0 events happening, and at time T plus H, you had that NT plus H equal to NT. Okay, in other words, they're both equal to 0. And we don't have this case anymore where NT is equal to something else like J minus 1, because that's not a possibility. Okay, in this case, J is equal to 0. So we don't have the other situation where NT was minus 1 and NT plus H could be the time where we added 1 to get to 0. So this is the only possibility, and I add plus O of H, which again we will get rid of. Okay, so this becomes easy, and this is just simply because these two events are independent. The first probability is going to be P naught of T times by, and then the second probability is NT plus H minus NT is equal to 0. That's the event, right? So that we're looking for. And we know that that is simply equal to 1 minus lambda H plus O of H. So I'm just going to take that O of H term and put it out there. Okay, now same story. Let's calculate the derivative. So let's take P naught of T plus H minus P naught of T and divide by H. What do we get? Well, in this case, that's going to go to the left-hand side. So we're going to be left with minus lambda times H divided by H times by P naught of T. So that's just minus lambda times P naught of T after dividing by H plus O of H over H. Okay, again, now taking limits, taking the limit as H, so you can say taking limit as H tends to 0, we get that the derivative of P naught of T is equal to minus lambda times P naught of T. Okay, so now for case 2, we need to go and check again testing equation 4.2. So let's now do that in green. So test equation 4.2 for case 2. Great, let's just do that quickly. Okay, so we have P naught, we need to check. Remember the 4.2 says Pj of T is equal to e to the minus lambda T times lambda T to the power J divided by J factorial. Okay, so let's test P naught. From what we get, the derivative of P naught, so P naught of T from equation 4.2, P naught of T is going to be equal to e to the naught, which is 1, right, times by naught. Sorry, I'm talking nonsense. So P naught of T is going to be e to the 0 times by, where have I gone wrong? E to the, sorry, T is not naught, J is naught. Okay, so this is going to be e to the minus lambda T times by lambda T to the power 0 divided by 0 factorial. Got it. Okay, so this is just going to be equal to e to the minus lambda T. And now we need to test whether that matches what we came up with for the derivative of P naught, well, let's calculate it. If we take P naught prime of T, well, then we simply get minus lambda e to the minus lambda T, and ta-da, that matches what we got there. Okay, so this is equal to minus lambda times P naught of T, which is what we got as differential equation. So that's as required. Now remember, we also have to test the initial condition, and that's quite easy because P naught of naught. So I'm just going to say, and P naught of naught is equal to e to the minus lambda times 0, which is e to the power 0, which is equal to 1 as required. Okay, so we've done now all the possible cases for J, and we have proved that, okay, the probability of NT equal to J follows that equation 4.2, because we've derived from first principles, we got the derivative of Pj of T, and we showed that it then meets that equation. So when we solve for the derivative, we showed that we do get that probability. Okay. So let's just complete this by saying this concludes our proof of claim 1. Now we kind of have almost like a corollary. So I'm going to write in orange, and this is, let's just call it claim 2. So claim 2 is saying more generally. So remember, what did we prove in claim 1? Let's just go back. Claim 1 was that NT follows a Poisson process with rate lambda T. So what is claim 2? We're saying more generally, if we just take any NT plus S minus NT in this process that we defined, then we will get a Poisson random variable with rate lambda times T. Lambda times, so that should be, if we want to write lambda T, then I would just have to write NS there. Okay, so make the increment, the increment time interval T. So that will be Poisson with rate lambda T. Okay, well, this claim 2 follows almost immediately from claim 1, because we have the proof of this is simply, well, firstly, note that the increments of the process NT, right, which you can just write N or NT with T greater than 0 if you want. So the increments of this process are stationary. How do we know they're stationary? Well, here it is. In our definition, we define them to follow exactly this distribution, right? So they will always follow exactly the same distribution regardless of the past history of the process. This will be the probabilities of those increments. Okay, so we know that they are stationary. Okay, so that's given. Whoops. Okay, given by definition of NT. Okay, so that's the first thing. And the second part of this proof is saying, well, they're also independent of the past. So these increments are also independent of the past. Where do we get that? Well, again, by definition, look at what we said. These increments, no matter what happened in the past, will always follow this probability distribution. Okay, so they'll always have this probability of being 1 at the top and this probability of being 0. In other words, the probability depends only on the time, the actual increment time, the H time units. Okay, so that means the increments are completely independent of the past of the process, and therefore this is also given. Okay, so I'm going to say also given by the definition. And then we have it, right? Because now we're saying that we have a stationary distribution. In other words, the increments are all follow the same distribution and they're all independent of the past. So I can actually just rewrite nt plus s minus ns, right? So that t time units is actually going to follow the same distribution as, so it follows the same distribution as nt minus n0, right? Which is just nt, which we have just proven follows a Poisson distribution with rate lambda t. And that is the end. This concludes our proof of claim 2. Okay, and that is the proof of how we are essentially showing that these distributions of this Poisson, these increments, sorry, of this Poisson distribution that we defined end up following a Poisson process with lambda t. Okay, and then that combined with the fact that they all follow, they're all independent of the past of the process, and that they start off with, that they meet the boundary condition of pj naught equals to naught in all cases. So the case where j was positive and the case where j was equal to 0, that all of those information put together, if you had to write a proof that says prove that those two, the chapter 4 definition and the chapter 1 definition are equivalent, you would add those lines to say, okay, well, from all of this information, we've proved that n0 equals 0, we've proved that the increments are independent, and we've shown that the increments follow this Poisson distribution with rate lambda t, and therefore our definition is equivalent to the chapter 1 definition. I hope that proof was helpful. Thank you very much.